section. I was just looking for Dr. Sethuraman, who is supposed to introduce the Tamil Nadu Science Forum.
Yes.
So he's not available. You have to do both.
Oh, just a minute. How do I reduce this thing? Yeah. Okay. Yeah, I'm all set.
Okay. So let's start now. So, friends, welcome you all. So, on behalf of Tamil Nadu Science Forum and the Popular Science Lecture Group, I extend my warm welcome you to all. Today we are going to have a lecture on the story of our star, the sun. This lecture shall be delivered by Professor Dr Nandi. We have with us Dr. TRG. So this meeting shall be in English. We would like to have a brief introduction about Tamil Nadu Science Forum and the PSL. So I'm expecting Dr. Sethuraman to introduce Tamil Nadu Science Forum, but obviously he's not here. Our speaker shall be introduced by Dr. Shubhastri Desigan. After that, the speaker will talk about 40 to 45 minutes and we'll have a question answer section. So we'll try to wind up the session by 1 p.m. So coming back to PSL, PSL is part of Tamil Nadu Science Forum and it started functioning in 2018 only, although TNFSF is functioning from 1980 onwards. PSL came into existence when we decided to strengthen the activities of TNSF in the higher science area. We have conducted 48 lectures so far, and this is our 49th lecture. This is held, the first lecture was held in July 2018 as Stephen Hawking's Memorial Lecture. PSL used to have its lecture in the hall and it adapted to virtual meetings during the pandemic period. We hope we may have few more meetings until the things become fully normal. Some of the participants are shown by the device name. We request you to change your name by right-clicking the icon. So we will mute all the mics except the speaker and request all of you to raise your hand when you have a question. When the question session starts, we may unmute the mic of those who wish to ask direct question to the speaker. So this is the ground rule. We would like to get the feedback on the seminar from you, and we are going to post a Google form. Please fill up the Google form and provide your feedback. This will help us to improve further. Please fill up the. We also keep your contact. We want to keep your contact details. Provide your contact details in the chat box, and you can also become a member of our Popular Science Google group. So it's popular-science-lectures plus subscribe at googlegroups.com. If you send a blank mail, you'll become a member automatically. Otherwise, if you send a mail to a email ID, we can include you in the mail in the Google group. We also have the Telegram group meant for PSL. So we are going to provide the link for that. So with this, we'll get into the introduction of Tamil Nadu Science Forum. Tamil Nadu Science Forum was formed by a group of scientists and students and researchers in 1980. It was started organizing science lectures and hall meetings in university campuses. So later it started going out of the campus and start doing popularizing the science to the common man. It went outside and in the form of drama and other things. No, we start doing it, and it get involved in the literacy movement, the functional literacy movement. Tamil Nadu Science Forum was one of the pioneer in making the literacy movement in Tamil Nadu a great success. So apart from that, now it has been grown into all district, and we have a full-fledged functioning state body and district bodies in Tamil Nadu, and it is functioning in 6 different verticals. I would like to say mention the few. One is the science popularization, and we have science publication, and we have another vertical called development and environment. And we also work for women equality and science for youth. And the last one is the education. 6 different verticals we are working on. We have 6 different functional groups throughout the state. We have it's available. So in each district, these functional groups are directly aligned with the individual verticals and carrying out the activities. PSL is part of science popularization activity. And we, before ending this introduction to Tamil Nadu Science Forum, I want to highlight a couple of points. One is now the TNSF is bringing out 2 important magazines, one for children. One is Tulir. This has been publishing for the last 35 years without any advertisement. And the second one is the Jantar Mantar in English. One is in Tamil, other one is in English. We also have several other, a couple of other magazines meant for the teachers and other things. We have a science publication area where we brought a lot of small books on science, particularly in local language. So these are all the 2 important activities that is fall under the categorization of science popularization. So with that, let me ask Subhasri to introduce the speaker.
Thank you, Vijayan. Actually, all the participants are inside. Have they been allowed inside? Because I keep getting messages saying someone is in the waiting room.
I don't see anyone is waiting.
Okay. Then we can, I'll give a brief introduction to I'll just read out the biography of Professor Dibyendu Nandi. Dibyendu Nandi is a professor of physics and currently the head of Center of Excellence in Space Sciences, India, CESI at IISER, Kolkata. He specializes in understanding the sun's dynamic activity and its influence on our near-Earth space environment and planetary atmospheres. Dibyendu obtained his PhD from the Indian Institute of Science and subsequently spent 7 years in the United States working at the Solar Physics Group in Montana State University. He has held positions at Harvard Smithsonian Center for Astrophysics, St. Andrews University, Georgia State University, and the Nordic Institute of Theoretical Physics. Dr. Nandi has published widely, including in journals such as Astrophysical Journal, Astronomy and Astrophysics, monthly notices of the Royal Astronomical Society, Geophysical Research Letters, Nature, and Science. Dibyendu's honors and awards include the Martin Foster Gold Medal for the Best Thesis from the Indian Institute of Science, the Karen Harvey Prize of the American Astronomical Society, the Young Career Award of the Asia Pacific Solar Physics Society, and the Modali Award of the Astronomical Society of India. Dibyendu is a co-investigator on the Aditya L1 space mission, which will be India's first space observatory to study the sun. He is currently the Vice President of the Commission E4 of the International Astronomical Union, which seeks to understand the impact of solar and stellar activity on planetary and exoplanetary environments. I'd like to say, I am a science journalist. I have written a lot about Dr. Nandi's work in the Hindu, and it's most fascinating how they try to model the corona and all that. But now I will leave I will not take more time. I will just say thank you and welcome to the talk today. Dr. Nandi, I think you can continue.
Thank you, Shubhasri, for your generous introduction and to the Tamil Nadu Science Forum for this invitation. As I was telling your organizers earlier that this is the first time that I'm speaking in a forum of science population in Tamil Nadu. I'm very excited about this, and I'm very happy that you invited me for this lecture. So I'm going to be talking about our star, the sun, which gives us life, but also has some dynamic activity, which is very important because it is hazardous to our space-based technologies. I shall also be talking about, in the context of the sun itself, the birth and death of stars, so as to give you an idea of the astrophysical ecosystem we share and the implications of the activity and evolution of a star for the future of humanity. I must first apologize about the way that the slides are working out here, because I understand that there is an issue and I cannot be full screen somehow. So you're really seeing the PowerPoint backdrop. So what I'm going to do is I'm going to just switch between slides manually. So I hope that you can now see my second slide. I don't know if it's full screen or not, but I hope you can see it.
Yes.
Yeah, so a little bit of background about me. So I come from the Indian Institute of Science, Education and Research in Kolkata, where I'm a professor of physics. So ISER Kolkata is an institution where we have undergraduate and PhD programs, as well as integrated PhD programs for various levels of students, starting from when they pass out of the school, senior school, class 12. That's the integrated BSMS program. We have the MS and the integrated PhD program for those students who have a bachelor's degree in the sciences or engineering. And then we have a PhD program for those who have a master's degree in science. You're welcome to look at our website, www.isercol.ac.in. And the center I lead, the website of that center is www.sesi.in, and you can look at our activities there as well. And we have a master's in space physics program and a PhD program at the Center of Excellence in Space Sciences. So if there's any students here, I welcome you to go ahead and have a look at this. Now, our general idea of space is that it is a vast, empty domain. And our story begins there. And I would like to, in today's talk, drive home the point that we do not exist in isolation on Earth as a body which doesn't interact with the surroundings, but rather a planet like Earth exists in an environment that is continuously changing and is governed by the variable and dynamic activity of the star that hosts these planets. And therefore, we actually share an astrophysical ecosystem. And the possibility of life, the eventual fate of life in any planet is intimately linked to this astrophysical ecosystem or environment that we share with our parent star. Our space is not a vast, empty domain, as often is the impression that most of us have. In fact, it is dynamic. And to prove that point, I want to show these observations from the Ooty Radio Telescope, which is located in Tamil Nadu. It's unfortunate that you don't see the full slide. And if you could, then I think you would have seen the dynamic variations in the background. So what you see in this slide is the sun at the center and the Earth in its orbit. Those two are superposed on the background observation. What this background observation shows in color is the density fluctuations of the plasma material that fills up the interplanetary space. And this plasma material has its origin in the solar outer atmosphere, which is known as the sun's corona. And it's varying dynamically, it changes all the time. So the sun's radiation output, particle output, there is a plasma wind output from the sun, which is continuously changing. And this changing space environment impacts and modulates the Earth's atmosphere. So what I would like to do before I come back to the sun is to give you a brief history of the universe and the birth of stars, so that we can set the sun in the context of other stars in the astrophysical universe. So as you know, in the beginning, there was what is known as the Big Bang. I'm not an expert in this field. There are many things about the Big Bang that you do not understand, but you understand that the universe began in this very highly intense, small, almost like a singularity kind of space, which was essentially a very dense, very hot region from which the universe started expanding. In the first really tiny amount of time, there was a rapid expansion of the universe because of this very high temperature, high pressure driven dynamics. And this phase is known as the inflationary period of the universe. But following about 300,000 years, the plasma material in the early universe, made up of electrons, protons, started combining, and with neutrons started forming the first neutral atoms in the universe. And that happened about 300,000 years after the Big Bang. This is when the light decoupled from the matter, and the universe, which was opaque until then, it was a hot plasma soup and opaque to radiation. The universe allowed the passage of radiation or photons. So when you probe back in the past to the early history of the universe, we're really looking at something like 300,000 years past the Big Bang. And eventually, after about 1 billion years, what happens is that the neutral atoms start clumping together, attracted by gravity, and forming the first stars. That happens about 1 billion years into the age of the universe. And then we have the system of stars which go through their life cycle. And about 10 billion years, we have the first deaths of star occurring. And I'll talk a little bit about how stars die in this massive explosions known as the supernova explosions. And it is very curious and interesting that when stars die, they spew out this material, elements, out into the universe and mixes it up, from which other stars form, other planetary systems form. And it's this elements which is essentially mixed or thrown out into the universe during the deaths of the first star that contains the materials which are very, very important for the formation of life as we know it. So in the death of the first stars lies the seeds of humanity or life. And I'll talk a little bit about that as well as we go on. So let me talk a little bit about how stars form. So see, there are really some competing forces here. So when you have masses, clumps of material together, you have gravity acting, and so these masses are trying to be pulled together by gravity. So essentially, a gravitational force is an attractive force which would like to clump together material and build bigger and bigger masses like stars, right, or galaxies, or even black holes. But then there is a competing force, and the competing force is the outward force due to the gradient in pressure. And that happens because when you are putting together material, you are building up pressure and temperature, and there are higher frequencies of collisions. And this collisions essentially is building up pressure inside this material. And the pressure is trying to push this material apart. It is acting against gravity. So gravity is trying to build matter, whereas the internal temperature and pressure of this astrophysical objects that are starting to form is trying to push out the material. So when gravity wins, you have the formation of a star. But then you can ask the question, why is it that you don't necessarily have everything contracting and becoming a singularity? Why is the sun holding its shape? And we'll come to that answer. That is essentially because of nuclear fusion, which generates enough energy that eventually the force due to the outward pressure gradient manages to balance the gravitational attraction, and you have the formation of a stable star like the sun. So when you look at an actual image, this is from the Hubble Space Telescope, you are looking at the large Magellanic Cloud. And this is a very interesting system because in this system, you see the distribution of large tracts of interstellar gas, which are essentially materials from which stars eventually form because of some instabilities, gravitational instabilities, that bring together this material and start forming denser and denser cores, which are known as protostars. So essentially, it's like a baby star from which eventually a system like the solar system is born with the sun at the center and some material forming planets which orbit the star. So what this image shows you is this bright regions are intense star forming regions when new stars, which are extremely hot and luminous, have been formed. And in the background is the material in this diffused brown color from which the stars are forming. So I really like this image because this kind of tells you about almost like a nursery of stars, which is being birthed as we see this, and we see this in evidence. This is happening in front of our eyes, far away somewhere in the universe. And the solar system was essentially born in this way through the formation of a protostar and a star in the Milky Way. Now, when we come to the building blocks of the universe, when you have at the Big Bang, you have this fundamental really tiny little particles from which you start building electrons, protons, neutrons, and they combine and they form the first atoms. The easiest atom to form is the hydrogen atom, where you have a proton and you just have an electron which is orbiting around the proton, held together by various sort of forces. One of the important forces in these dynamics is the Coulomb force. So you have only one proton in the center of a hydrogen atom. But when you start to build higher mass elements, there is a difficulty there. And I want you to appreciate the difficulty here, because this is something that really brings in a lot of different elements, astrophysics, particle physics, and eventually what forms materials like what you see me here, what we are made of, right? Okay. So when you have a proton already sitting in the center, take for example the helium atom, and then you want to bring in another proton. There is a repulsive force from the fact that there is already a positive charge sitting in the nucleus, and you're trying to bring in another proton into that domain, right? And so therefore, the incoming proton must overcome what is known as a Coulomb barrier, or the force of repulsion between two positive charges. So if you look at it technically, you have this sort of a barrier, which is known as the Coulomb barrier. And the incoming proton that is coming in has to overcome this barrier, which implies that it has to have energy, which is higher than the potential energy corresponding to the Coulomb barrier, which is trying to keep away any other positive charge from approaching the atom, the nucleus of the atom at the center, right? So which means the couple of things have to happen. One is that this proton that's coming in has to be very close to the core of the nuclei, which means you need to have a very dense, high pressure region. Number two, the incoming proton has to have a very high energy. So it has to come in with a very high kinetic energy that endows it with some ability to overcome this potential barrier. It has to exceed this energy to come in and go through and clump together with the nuclei and add to the mass of the element, thereby forming higher and higher mass elements. So that implies you also need very high temperatures in the region where you can start building higher mass elements, higher mass atoms, right? Turns out there is something else, a phenomenon known as quantum tunneling, which comes to the rescue. So even if classically the kinetic energy of the approaching proton doesn't have enough energy to overcome this Coulomb barrier, quantum tunneling endows it with the probabilistic possibility of tunneling in through the barrier to some protons and then fusing with the nuclei and thereby forming a higher mass atom. And this is how we form, through nuclear fusion, higher and higher mass elements inside of stars. And when nuclear fusion occurs, there is a certain mass deficit not all the mass that comes in is eventually utilized to form the final atom or element. Some mass is lost, and following Einstein's prescription, this mass deficit is converted to energy. E is equal to mc square, and this is fundamental to the life of stars, because this is what holds stars together. If you did not have this energy being produced in the center, you would not have this humongous pressure and temperature gradients that is required to create an outward force to hold the star together against any further collapse. So number one, the fusion produces enough energy for the star to hold itself together and form a sort of a stable period, which is known as the main sequence lifetime of a star. And the sun is in the midlife of its main sequence lifetime, over which its activity in terms of its evolution is more or less stable. And I will talk about that in a greater detail later. Number two, this energy that comes out of the star is eventually, first in the core is radiated out through the radiative zone, then is convected through plasma motions in the outer layer of the star known as the convection zone. And finally, when it reaches the surface, this energy is radiated away. And this energy is eventually what drives the atmosphere and climate of planets. And this is the energy that provides the basis of life through photosynthesis, and also provides, if you are at a particular distance, which is known as the Goldilocks zone, provides the right conditions in terms of temperature range, which is suitable for life to evolve and form. So this is the interplay of physics, not necessarily in great technical detail, but hopefully at a level that you can appreciate, which eventually results in the formation of a stable system like a solar system, with our star, the sun, at its center, with planets around it, which orbits around the star, and which provides the necessary condition for the star at the center to be a stable star, and for it to provide the energy to drive processes that are important for the sustenance of life in planets. So essentially, if you look at the interior of the sun, this is what is going on. At the core, the hydrogen that is in abundance and a little bit of helium from the initial collapse of a protostar to form a star like the sun is fusing to produce higher mass elements, multitude of elements that is produced in the interior, helium, carbon, nitrogen, beryllium, lithium. Many of the lighter mass elements are actually produced in the sun. And then this hydrogen fusion releases energy, which is radiated away first through the radiation zone. And then the plasma becomes opaque to this radiation or the passage of photons. So the photons cannot travel freely. So they sort of are absorbed here by the plasma, which gets heated up. And when you hit a material, and gravity is sort of pointing downwards, that material which becomes lighter because it's hot and less dense, it expands, becomes lighter, and it moves up. I mean, many of you are aware of the Archimedes principle, right? So lighter, hotter material moves up to the surface, thereby transporting energy to the surface. And that is why the sun radiates. And you see the radiation of the sun, you see photons and light from the sun. And once this plasma material on the surface has radiated away its energy, it becomes cooler and therefore denser and sinks back again. But then again gets heated up in the bottom layer. And this motion, up and down motion, keeps on happening, and this is known as convection. This happens in a pot of tea that you're cooking, or in a pot where you're cooking your samar. It happens in the Earth's atmosphere, and for the sun, it's fundamentally important because when you put together plasma, which is ionized matter, and the motion of this ionized matter in the convection zone, you really are sustaining large electric current systems. And from the Maxwell's equation, it follows that this is a regime where you can then have inductive effects which can produce magnetic fields. And I'll be talking about magnetic fields at some length because that has this other interesting dynamics that the sun produces beyond this sort of interplay of particle physics and gravitational forces and this pressure balance that I was talking about. Eventually, when a star is born, it's born with a certain amount of material. Eventually, the fusion reaction will exhaust the nuclear fuel. So the amount of hydrogen that was born with is finite. It is not infinite, right? When that happens, this high temperature, high pressure that was being sustained in the core and the pressure gradient, which was sustaining outward sort of force to balance the inward attractive force due to gravity, that balance is going to get disrupted. And so there is going to be a phase, a rapid in terms of not human scales, but astrophysical scales, evolutionary phase, where the sun will contract first and eventually become a red giant. I'll talk about that in greater detail in some time. But when the star is much more massive than the sun, not a sun-like star, but a much more massive star, at least, let's say, exceeding the Chandrasekhar mass limit, what happens is the evolutionary process when the star runs out of nuclear fuel is not as benign or as simple as what would happen to the sun. For more massive stars, the death of a star is much more violent and results in what is known as a supernova explosion. So what you see here is a supernova shockwave, again observed by the Hubble Space Telescope, which is emanated out of the death of a star, which eventually forms a neutron star at the center. And the outer part is blown away in this very violent process, forming shockwaves which throw out the plasma material and the elements, the ionized materials, the nuclei of certain elements which have been formed inside of stars throughout its neighborhood. So it distributes the material that has been formed due to nuclear fusion in the interior of this massive stars in the universe. And this process of supernova explosions is fundamentally important because it is believed that this process eventually seeds the elements that find its way into the formation of cells and human bodies. For example, iodine is a material that is actually produced and synthesized in this kind of a process. And iodine is something that is very important because it is in your thyroid gland. And it is amazing that these elements that play such an important role in our lives, in our sustaining life, are formed inside of stars, and through the death of stars are mixed together in the universe, through which the seeds or the materials of life come out. So this is the secret to the periodic table that most of you are aware of. And you're also aware of this famous remark that the cosmos is within us. We are made of star stuff by Carl Sagan. You see, so hydrogen and helium here, the lighter elements existed after the Big Bang, after the 300 years of the Big Bang. But then most of the other elements, the lighter elements, are formed inside of stars like the sun. The heavier elements are synthesized in larger stars and in supernova explosions and get mixed up in the universe. And many of these elements have found their way to the Earth, right? And have found their way inside our bodies. This process started with the Big Bang, with the synthesis of atoms following 300,000 years after the Big Bang, the formation of neutral atoms, with the formation of stars, with the initiation of nuclear fusion, with the loss of nuclear fuel and the explosion of stars in supernova explosions. mixing up of the material in interstellar medium, and the rebirth of stars like the sun and planetary systems from that material, which has eventually led us to where we are today and has formed beings like us. So it is actually, I find this incredibly amazing when you think of all these processes, which is not just one science. I mean, in this, there is so many sciences all put together, which has eventually led to life. Let me now go back to the sun. Having told you the story of how stars are born and how they die, let me go back to the sun. And why it is important for us to understand the sun in a more immediate context, in terms of context of days, years, 10 years, time scale. What I was talking about are very important aspects for us at a philosophical level, at a scientific level, at a long-term level. But how about applications of this at a short-term level? And let's talk briefly about that. Why is it important for us to understand solar activity? Okay, so the sun is a very active star, which is not just radiating photons. As I said, the outer part of the sun's convection zone consists of plasma material, which is in motion. And this plasma material is moving around through this convective motions and other motions like rotation and a circulation known as meridian circulation. And all of this contributes to a process which is known as the dynamo process, which is the reverse of what you see in the typical fans that you have in a hot, humid day like this today in Calcutta. My fan is running overhead, where you are converting electromagnetic energy to kinetic energy, right? And that's how the fan is moving, and we feel comfortable. So to the reverse, you extract the kinetic energy of the plasma to produce, and the electric fields that are there, the currents that are there. You extract that energy, that kinetic energy, to produce magnetic energy. And this happens inside the sun in the convection zone. And the sun produces magnetic fields which are concentrated typically in these regions which are dark. These are known as sunspots. You see this region here. These are sunspots. This image is from the Hinode satellite of the Japanese space agency JAXA. And the sunspots are regions of very strong magnetic fields on the order of few thousands of Gauss, which is about 10,000 times stronger than the Earth's own magnetic field. And sometimes the magnetic fields associated with these structures gets destabilized and form what are known as solar flares. Solar flares are very energetic events where the magnetic fields are disrupted and the magnetic energy is converted to produce thermal energy. And this is eventually converted to light energy. And these photons are extremely high energy photons. So there is radiation in X-rays, extreme ultraviolet. The energy is also used to accelerate particles. And when the flare is very strong, it accelerates a large amount of plasma overlying this regions which are known as sunspots. They accelerate the plasma so much that they attain escape velocity, and they are thrown out of the sun. And on this cover image of the National Geographic, you are seeing this violent ejection of the plasma material from outside from the outer solar atmosphere, which is known as the corona. And these are known as coronal mass ejections. And these are often associated with the most strongest of flares. Typically, each of these events produce energy equivalent of about 500 million nuclear explosions happening at the same time. That is the amount of energy that is contained in the storms. And you can imagine then that these are extremely energetic events, which has a bearing if they are directed on our space environment. If you look at the sun, we have observations from other satellites like the Solar and Heliospheric Observatory of the European Space Agency. So what you see here are regions which are known as sunspots, which I've just talked about. Those regions are also associated with very bright structures in the outer solar atmosphere, which is known as the corona. And so when there are more number of sunspots, the sun becomes a little bit more brighter. When there are lower number of sunspots, the sun is not as bright in its radiative output. And that's important, and I'll talk about the importance of it in some time. Okay, so when this solar energetic particles and storms interact with the Earth's outer atmosphere, one of the lovely things that it creates is known as auroras, or northern lights when it happens in the northern regions, or southern lights, which is Aurora australis, which happens in the over the southern poles. These are essentially these energetic charged particles from the sun's plasma winds and from the solar storms, which come and interact with the Earth's upper atmosphere, energizing the atoms. And when they come back to ground state, they radiate and you form this beautiful light, which light up the sky in the form of auroras. But the solar storms have a big impact on our technologies as well, which is something that is why it is very relevant from the application perspective. So, for example, when you have the impact of an Earth-directed solar plasma storm, many things can happen. First of all, it can impact the sensitive sensors of satellites, which is up in space, and make them malfunction. It can increase it can result in atmospheric heating and increase the density of the upper atmosphere where low Earth satellites are orbiting, therefore increasing the frictional drag on satellites, which results sometimes in the satellites deorbiting and being lost. Just 2 months back, on February 4th, this is exactly what happened to the SpaceX Starlink satellites. Starlink launched 49 satellites. They're trying to fill up our near space with multiple satellites to be able to stream high-speed internet. So out of the 49 satellites, 40 satellites were lost due to this drag-based deorbiting, unfortunately, because the launch coincided with multiple hits of solar storms exactly during that phase, which created these geomagnetic perturbations and the heating in the Earth's upper atmosphere, leading to an increased drag and loss of the satellites. In high latitude regions, the solar storms induce geomagnetic storms or geomagnetic perturbations, which rapidly results in rapid fluctuations in the Earth's magnetic field, resulting in induced voltages and currents through large conductors. Large conductors could be electric power grids, which are connected across very vast domains of lands, or oil pipelines, for example. So in 1989, a major solar flare actually took off the North American power grid around Quebec, and Montreal, the city of Montreal, was without power for about 3 days. And this is something that is extremely significant impact. When you're flying over the polar routes, the polar regions of the Earth are more susceptible to solar storms and the solar plasma coming in lower into the Earth's atmosphere, because the Earth's magnetic field lines near the poles are pointed outwards. So the Earth's field is dipolar, so near the polar regions is pointed outwards. And so this outward fields connect with the interplanetary space environment through which the solar plasma can rush in. And so the impact of this changing space environment, or space weather, as we call it, are felt in the polar regions much more in the Earth's atmosphere. So if you're flying over the polar routes, aircrafts are very, very dependent on sensors. And not only that, the pilots rely on high frequency communication with ground stations, with their handlers to ensure they're on the right path. They depend on sensors to measure the speed and altitude, which are also extremely important for safety. Whenever there's a storm, an intense geomagnetic storm, you don't want to fly over the poles. You want to go around. Now, that was the case early on. People avoided flying over the poles simply because there was no understanding of the impacts and no capability to predict solar storms. But over the last 20 years or so, we have developed capabilities to try and predict solar storms. And this has allowed larger and larger number of flights over the polar routes. As you see here in this bar, small little bars, the number of polar air traffic has increased. Why is this important to be able to fly over the poles? So if you're flying from New York, let's say New Delhi to New York, right? Now, on any sphere, if you try to connect 2 points, you want to really go through what is known as a great circle, okay, connecting these 2 points, because that's the least distance between 2 points on a spherical surface. So that least distance means lower fuel, and therefore all airline companies would like to do that, and therefore the tickets are cheaper. If you have to fly around low latitudes while going across the globe, that's not a very economical thing to do. So therefore, this also has bearing for the civil aviation industry. And of course, you can ask this question that, okay, I'm not flying. I'm not a high latitude country. I am just sitting here. Let's say in Chennai, I am not interested in traveling to other countries. Am I impacted by space weather? You are. If you are using a satellite dish to stream your TV broadcasting, if you're using a mobile phone, for example, for communicating with somebody who's far away, not within the reach of the same mobile tower that we're in there, if you're using GPS navigational devices, because all of this communication happens between the mobile tower nearest you and through space where a satellite is sitting and communicating back that signal through to another mobile tower from where it reaches the person you're talking to. Navigational networks depend strongly on a suite of navigational satellites which are placed in low Earth orbit, which triangulates your position and tells you where you are and can map out a direction for you. So whenever there is a solar storm, there are errors that happens in navigational networks. There are satellite outages. If there's this intense solar storm, not always, when there's a very intense solar storm. And there are also disruptions in telecommunications and high frequency communications, which a lot of defense agencies and emergency service as agencies depend on. So many of us today unknowingly are utilizing technologies which is based in space and is susceptible to the space environment or space weather, which is completely governed by the sun's dynamic activity. And therefore, even for people like us, normal people, it is so important to be able to appreciate what is going on in the scientific domain in trying to understand how does the activity, the parent star that we live around is impacting us. Let's talk about a little bit longer term. So when you look at the number of sunspots on the solar surface versus time, you have this plot, which is a sunspot time series. So on the y-axis is the number of sunspots, on the x-axis is time. And we have direct observations of this over the last 400 years, starting with the early pioneering observations of guess who? Galileo Galilei. And also others like Christoph Scheiner, Fabricius. They have contributed to this plot that we're seeing here, including Galileo Galilei. And of course, now we have modern observatories that is looking at this numbers and counting them. There are international agencies which are the bookkeepers of the sunspot number time series. you see that the amplitude of the sunspot cycle, there is a cycle. And typically this cycle is an 11-year cycle. It goes up and down, up and down. Okay. The amplitude varies from one cycle to another cycle. And while that variation is not very strong from one cycle to the next cycle necessarily always, over the long period of time, over 400 years, there is a large variation in the amplitude. And often you find, not often, but typically the statistic says you expect a few events like this in like a couple of events like this in every 1000 years. You have this phases which last for about, on the order of 50 to 100 years, known as solar grand minima phases. And this phase is when you have hardly any magnetic activity or sunspots on the sun. And the last such recorded event was known as the Maunder minimum between 1645 and 1715 AD. When essentially the sun lost its sunspot cycle. And very interestingly, this grand minima phase of the sun also coincided with what is known as the Little Ice Age on Earth. Here is a picture, it's a painting. And here where science mixes with some arts and culture and how you use this sort of history from other domains and connect it to the science that you are doing. And there are people who do that actually. Here is a painting from period, the Little Ice Age, by Henrik Averkamp, showing a river near Amsterdam, which is completely frozen. Okay. Now, typically an artist paints based on his imagination. So of course, one can have a fantastic imagination, but then rivers near Amsterdam never freeze. So this is not an imagination. He experienced this. That rivers that has never frozen has frozen over, and the people who are walking over on the frozen ice of the river. So the severest, the coldest part of the Little Ice Age, which is widely documented historically in Europe, coincided with the Maunder minimum. So people have then asked the question, is there a direct connection between what is going on in the sun and our climate? The question is relevant and also important. And herein are some clues to why it is important. So on the bottom plot here, this red curve that you see is the sunspot time series plotted over the last, I think from 1978, since when we have precise measurements of its variability for which you need to go outside of Earth, the satellite-based measurements of what is known as the total solar irradiance, which is the total energy from the sun that reaches Earth's orbit per unit time per unit area. That is not the total solar irradiance. On the top is the total solar irradiance. That's the energy that reaches the Earth orbit. On the bottom is the sunspot time series, is the variation in the number of sunspots over time plotted over the same period. And you see that tightly coupled. Whenever there are a higher number of sunspots, you have higher energy output from the sun. When there is a lower number of sunspots, there is lower energy output from the sun. Unfortunately, in the 1970s, the solar energy output, the luminosity was known as the solar constant. We didn't expect that it was a variable, but now we know that in fact, it is a variable. The sunspot cycle varies. The amount of radiation that is coming out of the sunspot cycle is also a variable. And this variable radiation from the sun is in fact the driver of the Earth's climate. Interestingly, in half an hour, the sun provides enough energy input to sustain the annual needs of humanity. That is the amount of energy that the sun gives out. Okay. And this energy is actually not a constant, but it is a variable. So the question then is there some connection between the energy output of the sun, the variable radiation output, and the global climate? Okay. And that has driven a lot of research in the last 50 years, because we have been trying to understand what is behind the rapid climate change and global warming that we have evidenced. What you see here is a curve, plot of two things. One is the global temperature anomaly, that is the blue curve. When you do a sort of a smooth fitting to that, you see that roughly over the last roughly 150 to 200 years, there's a rapid rise in the global temperature. And that typically gives rise to this, what is known as the hockey stick plot. Because if you look at this part of the plot, it looks like, a rapid straight vertical rise with a little bend, which matches with the earlier time, giving it the impression of a hockey stick, right? Now, if you look at the activity of the sun, that's the reconstructed. We can look at the reconstructed long-term solar activity over the last 1,000 years as well. That's the red curve here, and what you see here is this, that even the solar activity has increased over the last roughly 200-year time scale. If we just eyeball this and do what is like a chi by eye, you would jump quickly to the conclusion that I have two independent parameters. One is sorry, is there some question in the background?
No,
I think there's
some
something.
Could you, Sellakumar sir, can you just check and mute? Yeah.
Right. So if we just, and this is a mistake we often do. We see two parameters which are sort of moving up together or going down together, and without really establishing causality, we quickly conclude that therefore these are two interlinked parameters in the sense that one of this is driving the other. As scientists, we should do better, and these attempts have been made by people to do a better judgment of what is going on. So if we pose the question then, based on this, is the sun behind global warming? This question has now been conclusively answered by hundreds of scientists working together, building climate models with the solar energy input, with also the energy equivalent radiative energy input that is expected from the greenhouse gases. And I would like to explain this a little bit, because this is something that is fundamentally important to all of us to appreciate. I do not know, and I do not really understand whether you really see this plot, but I want to just make this plot bigger. And I again apologize that you're not really seeing it in full screen. So let me make this plot bigger. Okay. So what you see here is this. You're seeing the results of climate simulations. On the y-axis is the temperature anomaly. On the x-axis is years. Okay, all right. The blue curve that you see here is the temperature anomaly that you would expect only if you utilize the forcing or the input from natural radiative changes like the sun's radiative energy output variations. The pink curve is the curve that you expect to see from the simulations, where you include both the forcing from the sun as well as the equivalent radiative forcing from the greenhouse gases that humanity is producing. That's the pink curve. And now you put the observation here. What is the observed curve? The observed temperature record. That's the black curve. And now you see that solar activity variations alone cannot explain the rapid rise in temperatures that you have witnessed in the last 100 years or so. For that to be explained properly, you need to acknowledge and incorporate the impact of greenhouse gases. Now, of course, physical models beyond simple statistical correlations allows you to establish further causality. And now we know that the variations in the sun is responsible for less than 10% of the change that you see in the global climate record. most of it is actually because of greenhouse gases. Okay, and that is something that is a message that I want to leave you with, that the rapid climate change that's happening in the last 100 years is because of us. It is anthropogenic forcing which is dominant. Okay, so from this more immediate, more relevant applications of understanding our astrophysical ecosystem for humanity, I will move a little beyond now to a domain which will transcend science, our existence, and a bit of philosophy at that, which is the sustenance of life in planets and the role of the sun or stars in this process. Okay, when I have a planet, and as I have now, by now, I hope you appreciate that the most dynamically changing environment that is happening around the planet is due to the activity of a star. So not just the sun has this radiative output or radiation which is changing in time, which is driving atmospheres and climate. It also has this sudden energetic events which are known as solar flares or coronal mass ejections, which drive plasma at very fast speeds, on the order of sometimes reaching 1,000 kilometers per second, supersonic speeds, 1,000 kilometers per second. Please appreciate that when you drive a car, you are driving a car typically at speeds of 60 kilometers per hour. I'm talking here of speeds reaching 1,000 kilometers per second of magnetized plasma being spewed out of the sun, and sometimes it is earth directed and can hit the earth's space environment and its magnetosphere around which it surrounds us. Apart from that, there is a continuous stream of supersonic plasma winds known as the solar wind from the sun, which was predicted by Eugene Parker back in 1958, 57 or 58, I'm forgetting. In a classic paper, which he had trouble publishing. It was being continuously rejected by the journal, Astrophysical Journal. Chandra, you all know of. He is like home ground for all of you. Chandrasekhar was in University of Chicago at that point in time, and it's an interesting story. I'm just digressing, but when you give a scientific talk, it's nice to kind of digress into these beautiful stories. So Chandra was in University of Chicago, and his office was very close to the office of another very, very famous person called Eugene Parker, who actually was a pioneer in understanding the sun, and who predicted the solar wind. So Eugene Parker was just a couple of offices away from Chandra, and Chandra was the editor of the Astrophysical Journal. So Chandra walked in to Eugene Parker's office and said, "Hey, your paper is being rejected by multiple referees. You explain to me and convince me that what you've done, your calculations are correct." And Parker sat down and explained to Chandrasekhar his calculations. And the story goes that Chandra could not find a mistake in Parker's calculation. And although this whole idea that there is a supersonic stream of winds, plasma winds flowing out of stars, was extremely strange and revolutionary at the time, Parker's paper eventually got published because Chandrasekhar, who was the editor of Astrophysical Journal, overruled the referees and published that paper. In about 3 years to 4 years, when the first satellites were launched, they detected a supersonic fast wind of ions and electrons flowing past the near-Earth space orbit, which was indeed the wind that Eugene Parker had predicted. Anyway, that's a nice little story about scientific publishing. But anyway, so coming back, this wind is continuously impacting the Earth's magnetosphere. And the point is that when the sun was much younger, the winds and the storms from the sun were much more frequent and much more high speed, because the active sun, when it was younger, would have emanated much more stronger doses of radiation and this energetic particle winds. And so it's expected that they would impact the planetary atmospheres. So the most important dynamical phenomena that is naturally forcing planetary atmospheres is this radiation, storms, and particles, and the winds from the star. Okay, the question is, how are we protected from this? Well, we are protected from this because the Earth's atmosphere is cocooned or surrounded by what is known as the magnetosphere. The magnetosphere is produced by a dynamo mechanism inside the outer core, the liquid iron core, which is the outer core of the Earth, and this sustains a magnetic field. Now, magnetic fields are very good at trapping charged particles. So essentially, all these charged particles that are rushing in are being trapped by the magnetic fields that surrounds our atmosphere. If the Earth did not have a magnetosphere, then the solar plasma wind particles and the storms, which are extremely high speed, supersonic, would have directly interacted and impacted with the atmosphere. And what could have resulted from this interaction? To answer that question, we go to Mars, because Mars is a fantastic laboratory of what can go wrong in this case. Okay, and the question we pose here is, how does the changing activity of the sun and the changes in the planets themselves impact planetary atmospheres? So about 1.5 billion years into the age of planet Mars, we believe, based on certain scientific theories, that Mars had a liquid iron core which was rotating, and therefore it had a magnetic field, global magnetic field surrounding the planet, and a magnetosphere just like Earth. It is also known that around that time, because of the protective environment of the magnetosphere, Mars had sustained greenhouse effect, and had a warm, moist atmosphere, which could have been suitable for life. I'm not saying this is proof that life existed on Mars. All I am saying is that conditions were suitable for the possibility of life in Mars, existing in Mars. Now look at Mars at the present time. At this point in time, about 4.5 billion years into the age of Mars, the Martian dynamo has died down because the liquid core has cooled and there is no global magnetic fields. And neither does Mars have a global atmosphere anymore. It is a very thin, I think on the order of few hundred meters atmosphere, which is just very rich in carbon dioxide, which is completely unsuitable for life. So in between 1.5 billion years and the present time, Mars lost its dynamo, the global magnetosphere, and its ability to sustain an atmosphere, and also possibly the ability to host surface life. So this is a fantastic example of what could happen if we did not have a magnetosphere. And this is something else I want you to appreciate. Life is possible not just because of one thing. It is possible because of multiple different elements and signs coming together, including the fact that the Earth rotates. There is a liquid iron core where there is convection, which produces magnetic fields. And therefore, the Earth has a magnetosphere, magnetic fields, which is protecting the Earth's atmosphere from these violent solar storms and the solar wind particles from the sun. Okay, so now how do we explore the sun? We explored the sun through various ways. We explored the sun through computational modeling. One of the ways we computationally model the sun is to produce simulations which look at how does the sun produce this magnetic activity which drives the winds and also the strong stream of particles out of the sun. For this, we utilize models known as the Dynamo models, and these models are now sophisticated enough that it can predict future solar activity, which is very important for figuring out the space environmental conditions over the next decade and the climate forcing of the sun as well. So for example, you see here the result of a sunspot cycle simulation from our center, in which we predicted the next 10 years of solar activity. And this is how it's going to look like. So our prediction is the solar cycle 25, which is currently ongoing, is going to be slightly stronger than the previous solar cycle. So our computational models now allow you to reconstruct and compare. So the black curve is the observations, the red curve is the simulation. So you can compare, reconstruct the past history through simulations, also go ahead and predict what is going to happen in the future. That's one way sort of we look at the interior processes in the sun through computational modeling. The sun's outer corona is a super hot thin layer of plasma. And it's a very interesting region because you see these beautiful magnetic loops, which you do not see necessarily in any laboratory setting. And I'm not going to the physics of why you see them, but you see them. These are actually magnetic fields which are connected to sunspots, which are at the base, at the surface of the sun. These magnetic loops sustain what is known as magnetic reconnection, where some of the magnetic fields are destroyed and produce solar flares, solar storms, heat up the outer corona to 1,000,000 degrees, which is known as the coronal heating problem. And that strong heating increases the pressure and eventually contributes to the driving of the solar wind, this outward flow of particles from the sun. So we use computer models to understand the magnetic fields in the solar outer atmosphere, the sun's corona, and predict how it's going to look like. And solar eclipses provided a wonderful opportunity to actually compare your predictions to the structure that is observed on the sun. So for example, here you see again a simulation from our group where the lines, the background lines in different colors are the magnetic field structures. In the background, the white color is the light that is coming out due to Compton scattering from the corona. And this is something that you really see only during solar eclipses because we can block out, the moon blocks out the bright solar disk. And this provides an opportunity to see how well your models are doing compared to what the real coronal magnetic fields might look like. Okay, here's an interesting fact. So you see the solar corona, and here is what is the coronavirus. Okay, so the solar corona looks like that. Again, I apologize that my full screen mode is not working, so none of the animations are working. Here is the solar corona. And this solar corona has this structure, spike-like structures because of the coronal magnetic loops. And here you have the coronavirus. And now you know where the name coronavirus comes from. Unfortunately, this has sort of occupied most of humanity over the past couple of years. I tried to figure this out from a completely different perspective at the biological level, right? But it's this interesting connection, the solar corona and the name of the coronavirus. So the solar corona also hosts these magnetic loops, which sometimes flares. And when they flare, and there is a coronal mass ejection associated with this, you can actually image them through satellites. This is the LASCO coronagraph instrument, and it has blocked out the sun, the bright part of the sun, and you see these coronal mass ejections traveling out of the sun, these bright structures. This we actually predicted, this particular storm, which occurred between 2nd and 4th November 2021, and we dubbed it the Diwali solar storm, which did impact Earth as predicted and created severe geomagnetic storms and auroras. And we are proud of the fact that we are actually able to predict that. We have now the capability to predict the arrival times of such storms. Okay. We also do computational modeling at CESI. And again, I apologize that the simulations will not be working because I'm not being able to enter full screen mode due to some reason. And I'm not able to show you the simulations. But what we would have seen here, if you could see the simulations, is that this dipolar magnetic field structure of the sun that you have is impacted by the solar wind. And there is a bow shock region, which is created in this site, which stops the solar wind from penetrating deeper into the Earth's atmosphere. The Earth's atmosphere gets protected from the solar wind. And this dynamics is something that we can now simulate and understand in how the Earth's magnetosphere is interacting or being forced by the solar wind, and being able to still protect us. Okay, we also explore the sun through satellites. So this is a timeline on the x-axis, and here you see multiple satellites and when they're launched by space agencies like NASA, ESA, and some missions by the Japanese space agency. So there are at least 30 satellites now exploring the Sun-Earth system, looking at the activity of the sun and understanding the near space environment, how it impacts us. Because of the importance that these events, solar events and solar phenomena has in terms of impacting our satellite-based technology and our modern society, which all of us depend on, starting from GPS navigational networks, polar traffic over air routes, high-frequency communications, electric power grid failures, ionospheric and geomagnetic storms, all of this. So India is going to launch its first sun-observing satellite, known as the Aditya L1 mission, hopefully within the year. It's nearing completion. And this is a comprehensive solar observatory which will look at the genesis of, or the origin of solar magnetic storms and the solar wind in a solar corona. It will look at the sun's chromosphere, which is the layer sandwiched between the solar surface and the corona, through which much of the dynamics of energy transfer and magnetic field emergence from the solar surface into the corona takes place. There are multiple instruments on this mission, which is to image the sun from a distance. There are also multiple instruments on this satellite, which is going to look at the near space environment and measure the plasma characteristics at Lagrange point L1, which is a point which is a little bit away from the Earth, but along the Sun-Earth line. Once you're in this point, the gravitational attraction between the Sun and the Earth cancels out, and it's a very stable point. If you are able to locate a spacecraft there, it moves along with the Earth, along the Sun-Earth line, continuously as the Earth orbits the Sun. So you have the opportunity to continuously observe the Sun from there. Also, the opportunity to continuously downlink the data through telemetry to Earth. And so it's a lovely location for observing the Sun almost 24/7 throughout the year. And this Aditya L1 instrument is going to critically impact our ability to understand the origin of solar activity and its influence on near space environment and our technologies. We are also planning the National Large Solar Telescope, which is a 2-meter class telescope, which will be one of the largest solar telescopes in all of Asia, which we plan to install near Pangong Lake in Ladakh. This is a proposal under serious consideration right now with the government, and we hope that this will be funded, because this will also impact our ability to look at the interaction of magnetic fields and plasmas in very high resolution at small scales, which are the fundamental physical processes that govern much of the more large scale dynamics that I was talking about. Okay, I'm nearing the end, and this is where I have a little bit of philosophy for all of us. So the end of our star, the sun. So as I said, that stars are not born with infinite amounts of hydrogen fuel for powering nuclear fusion, right? Eventually we're going to run out of hydrogen fuel inside the sun. When that happens, suddenly you don't have that high pressure and temperature in the interior, which sustains the star against gravitational collapse. So the inner core of the star is going to immediately start contracting. When there is gravitational contraction, it releases energy. And this energy release is converted to thermal energy, which hits up the outer layers of the star. And the outer layer expands rapidly and massively. So when this happens to the sun, in about another 4 billion years from now, 4 or 5 billion years from now, the sun's inner core, which is run out of hydrogen, and eventually will also run out of helium and will become carbon rich because sun doesn't have enough temperature to burn carbon or produce sort of higher mass elements. There'll be carbon rich core left behind, which I will come to what it is. But while that process is going on, the contraction in the inner core, the gravitational energy released due to the contraction is hitting up the outer layers and results in the massive expansion of the star. And it becomes what is known as a red giant. The expanding red giant, the outer hot plasma material of the red giant, will eat up all the inner planets, Mercury, Venus, Earth, and go all the way up to Mars orbit or beyond. And this is a phase that will eventually not allow life as we know it today to go on any of the inner planets for certain. And also on the outer planets, because once this happens, the temperature anyway is cold in the outer planets, which is not suitable for life. It's going to become a very, very cold region. What is left behind in the center of that collapsing star, the sun, can be understood by looking at other stellar systems which has collapsed similarly. What is left behind is this tiny white dot that you see here, which is known as a white dwarf. Okay, the white dwarf, which is just contracted, is still initially hot and radiating, and it lights up the outer layers, the outer gas which has been blown away because of this energy released due to the gravitational contraction, and then there's some process called helium burning in the outer atmosphere, which blows away the outer layers throughout the solar system, and the solar system doesn't exist anymore. You have what is known as a planetary nebula, and this light from the dying star left behind in the white dwarf, which is still hot. It illuminates this outer layers, this beautiful sort of way, which is known as a planetary nebula. Okay, and eventually, this sort of beautiful image that you see is really signaling. This is a real image, by the way, a real observation by the Hubble Space Telescope. This really is signaling how our star, the sun, will die, and how humanity as we know in the solar system will possibly not exist. Okay, so what happens to humanity and life as we know it? And this is where philosophy comes in. We do not know. And if you see this image here, we are now into the realm of science fiction. This clip here is from Star Wars 4, A New Hope, where you see Luke Skywalker watching a double sunset. He lives in a planet where there are two suns around which his planet Tatooine is orbiting. And the question is, and this is a little bit of somewhere between science fiction and philosophy, can human beings, or whatever the form of human beings are, about 4 billion years from now, let's just say life, can life find another planet far away which is suitable for sustenance, for sustaining us, or sustaining the future of humanity? Is that something that is impossible? Well, I mean, if you ask me that question, I think it's possible. If you look at the last 50 years, just the last 50 years, we had nothing up in space. In the last 50 years, we have managed to send rockets and satellites up in space. We have managed to send human beings up in space. We have managed to send human beings to moon. There is satellites which has been sent to Mars and beyond. The Voyager missions have gone beyond the solar system and are out in the dark of space somewhere. If we have achieved that in 50 years, one can only imagine what can we achieve in the next 4 billion years. And I leave you with that hope and end with this last slide, which is really the concluding slide. Essentially, to recapitulate some points that I want to leave you behind with. Our star is not an exotic star, like a neutron star or a black hole. In the scheme of overall ranges of stars that is possible, it's a very ordinary star. But that ordinary star is what sustains life on Earth. And that is important for us to appreciate. There is also an intimate relationship between planet Earth and planets and stars like the Sun, which allows the process of habitability. And this is an understanding that we can take from the Sun-Earth system, the solar system, to explore other exoplanetary systems far beyond our own and assess whether we can find a planet that is habitable. And this is what drives this rapidly emerging field of exoplanetary sciences. So many billion years from now, if humanity still survives in some form, we'll be forced to find another home, which is way beyond Earth, and another stellar system where life is still possible because it's habitable, unlike the solar system, which will become habitable. There are, of course, many things that we do not know about the intricacies of this process, and there is something there that many of you as students who are listening here today can contribute, because these are profound questions that confront humanity. And I hope that many of you would be there in the future to be able to answer some of these questions, which determine something as important as our eventual fate in the context of the cosmos. And with that, I will end and leave you with this beautiful image of a solar storm, what is a solar plasma filament eruption happening in the sun with Earth to scale. This shows you how small we are in the overall scheme of things, of the stars and the vast cosmos that we live in. And I hope that I've been able to convince you about the fact that we don't live in isolation, but we share an intimate ecosystem with our astrophysical environment. Thank you very much.
Thank you, Dibyendu, for that excellent talk and the beautiful pictures, and also the thought that how life is so precious and it's a confluence of so many factors that has made life possible on Earth. The magnetic sheath and everything and so on. It's really been a very fascinating talk. I would like to ask you a couple of questions, but before that, is in the audience, if you have any questions, could you please raise your hand so that the moderators will let you in to ask questions? Vasant has a question.
Good morning, ma'am.
Good morning. Please address your question to Dr. Dibyendu Nandi.
Yes, ma'am. I have a question regarding the solar sunspot.
Yeah,
Yes.
go ahead.
The sunspot has, as Sir told that, sunspots have high magnetic field, and they are their temperature are very cool. Is there any connection between the high magnetic field and the temperature of the sunspot?
Yes. So it was a very interesting question, and I didn't really want to get into very big technical details about this, but let me go back to this picture here. So what you see here is this: that you see this sunspot structure, and the core of the sunspot actually is dark, and the core of the sunspot is dark because we have very coherent magnetic fields inside of sunspots. And if you look at the Navier-Stokes equation, which looks at the evolution or the dynamics of flows in the context of different forcing terms, and the equivalence of the Navier-Stokes equation in magnetohydrodynamics, which is the dynamics of magnetized plasmas, you realize that there are magnetic forcing terms sitting in that equation, which actually determines the evolution of velocity fields. Now, what are the velocity fields you're talking about? We're talking of turbulent convection, the convective flows which transports energy from the deeper interior to the surface of the sun, right? The magnetic forces that are relevant here are the magnetic tension forces. Magnetic fields do not like to be deformed because they have magnetic tension. And so they inhibit the plasma flows. There is a force acting against the plasma flows trying to deform the magnetic field. So convection, which is trying to deform the magnetic fields, is suppressed within the strong core of the sunspots where there are very strong magnetic fields. And because convection is suppressed, the transfer of energy from the interior of the star to the surface is also suppressed within the darker core of the sunspots. So they're actually little darker in appearance, right at the core regions.
And I have another question.
Yes, please continue.
Sir, what is mean by magnetic reconnection and how it affects the solar coronal mystery?
Right. Okay. So let me see if I have anything that I can use. Yeah, let me go to this image. So you see this magnetic fields, right? These are actually plasmas. What you see are really plasmas radiating, but there's this. Well, again, I don't want to be technical, but there is this. In the solar plasma, the magnetic Reynolds number is very high, and when you have systems where the magnetic Reynolds number is very high, the magnetic fields become frozen in the plasma flow in the plasma. So what you're really seeing is plasma, which is frozen in with the magnetic fields. So essentially, it's an indirect way of imaging magnetic fields. All right. Now let's imagine that I have magnetic fields, which is all pointed from clockwise, going up from the left to the right. So there is a peaceful coexistence of this magnetic fields. Now, if I have magnetic loops, which there are some magnetic field lines which are going clockwise from the left top to the right, and some fields which are going anti-clockwise from here the other way, and due to the plasma motions, you bring them together. Then you have regions where magnetic fields will get in touch and are pointed in multiple different directions at the same point. That is not allowed because divergence of B is equal to 0. And you cannot have magnetic fields pointing to multiple different directions. The way out for nature, when you manage to evolve the fields into a situation where you're getting in touch to oppositely directed magnetic fields together like that, is to completely get rid of this magnetic fields by the process of magnetic reconnection and reattach the field lines in such a way that when you bring a loop like this together, they get reattached and move away like this. And the central part, the magnetic field destroys. But then we know also that energy is conserved. So the magnetic energy that is the energy that was contained in the destroyed magnetic field is converted by the magnetic reconnection process to thermal energy, which heats up the local plasma, creating this bright sort of loop-like structures that you see as the hot solar corona. And so that is why even if the surface is 6,000 degrees Kelvin, the corona is 1,000 degrees Kelvin. And that was traditionally known as the coronal heating problem. And there is another way to also to heat the corona, which is if you have turbulent convection in the which is always ongoing in the solar interior, it literally shakes. You hold this magnetic fields and it shakes the foot points of these loops which are connected to the surface, and you drive waves through the magnetic fields into the corona. If there was a way to dissipate those waves through shocks in the corona, then the energy that you're transporting, the kinetic energy through the waves, is also dissipated in the corona to heat the corona. And that is thought to be another theory to heat up the solar corona to 1 million degrees.
And I have one more question.
One more question, Vasan. So can we just see whether there are other people? Then we can come back to you again.
Okay, ma'am. This is my last question.
Okay.
Sir,
okay, please go on.
As you told that our sun's fate is going to be fatal, and the earth cannot be suitable for life in next billion years, for the next billion years. At the end of the sun's life, it will expand, and the sun's surface will engulf the earth. And if that happens, the habitable zone of our sun will go further away, and we can can we have exomoons as a potential life spot for our future, like Saturn's moons and Jupiter's moon?
Okay, so exomoons are not moons in the solar system. Exomoons is a term that is used for moons which are around exoplanets outside the solar system. Life depends on multiple different things, including the distance of a planet or any moon or for the planet. Just let me just say object from the star. You have to be in the zone where certain conditions are satisfied. For example, a certain temperature range that life is used to. The possibility of liquid water as well. So the further you go away, those conditions become much more extreme. At Mars, for example, the difference between daytime and nighttime temperatures are extremely huge, which itself is a problem for even us to move there, unless you have, some ways of geoengineering or creating the structures that can have controlled environments. Beyond that, it's extremely difficult to find evolved forms of life in the moons of planets like Saturn's or beyond. Although we are planning satellites and probes into some of the oceans that exist to see if there is some form of primeval life forms that possibly can exist. But evolved life forms, it will be very difficult to sustain because you don't really have the energy in it. Remember that the white dwarf eventually will cool and there is no energy to sustain the atmosphere, no energy to draw upon, right? And sustenance needs energy. We need to have photosynthesis, right? All those things are gone. So therefore, the solar system is more or less, I think, out of the question for sustenance of life, unless there's some miraculous something happens that allows us to harness some different form of energy from some different source, which is far outside the solar system.
Nice. Thank you for the replies. Thank you. Thank you, Vasant, for the interesting questions. Aditya Nair has a question. Would you like to ask? You can unmute yourself and ask.
Good morning. Good morning, sir. I am studying in 9th standard. So, sir, I have doubt that means after the lifetime of our sun, the means outer layers will be like explored out into the means space because the gravity would like all the material except the core will be thrown away into the deep space. So the further planets like the Neptune, then Uranus and Pluto is a dark dwarf, and that's a different thing. But they will be like kicked out of their atmosphere orbit only because the gravity of the sun will decrease because its mass decreased, and also because of the explosion of the outer layers, some planets orbits will be shifted. Then would sun means able to like sustain a solar system?
Okay, so I will answer two questions at once. I think there was also another question in the chat box. What happens if the sun becomes a black hole?
Yes.
Well, so okay.
No, a star near the sun becomes a black hole.
Star near the sun becomes a black hole.
Will it affect our galaxy?
Okay, so yes. So speaking from the perspective of orbits and the stability of orbits, essentially when the sun loses its outer atmosphere and white dwarf is left behind, it will be, the white dwarf size will be the same size as that of Earth. So it will reduce in size to the order of like, about less than 10,000 kilometers in size. The mass that will remain is roughly, I think, half. If I recall right, roughly half of the current mass of the sun. So yes, the gravitational forcing will change and the orbital balances will be shifted. Okay. So that's one important thing that will happen. And it is possible that some of the very outer planets will no longer remain in orbit around the white dwarf. So that is certainly possible.
And for planets like Jupiter?
Every star's orbits will change somewhat because eventually it's the gravitational balance between centrifugal force and the gravitational attraction that is involved, and you're changing the central mass of the system, right? So it will all change. But the point that I'm trying to make here is we don't even know that the planets will survive at all in the form that we know them to be, right? The question you're asking is beyond that. But as of now, our understanding is the planets will not necessarily survive the red giant phase, at least the inner planets. Okay. Jupiter may, because it's still very large. But you're taking away the most important source of energy. And please don't forget that, right? That source is gone now. A white dwarf is not a sustainable source of energy. That's one important thing. Okay, there was another question: is what happens if there is a black hole formation somewhere nearby? It will not change anything. In terms of if there is no other dynamics other than just the formation of a black hole nearby, as long as you are well outside the event horizon, and well away from it, you are just sensing the gravity from a distance and will not change the overall gravitational dynamics. Okay. You may ask the question, what happens if there is a supernova? That's the interesting question to ask. What happens if there is a strong supernova that happens here? Will it wipe out humanity? I don't think it will. It will certainly have an impact because the large doses of radiation, the energetic particles, the cosmic rays that comes in, will certainly impact the Earth's atmosphere quite a bit. But I do not believe that it is something that can completely wipe away humanity, because our nearest star is still quite far away.
Which is is there a near star that
Proxima Centauri. Proxima Centauri. That's the nearest.
That can't become a supernova.
It will not. It will not. It is. I quickly cannot answer it because I need to know the mass of Proxima Centauri.
Okay.
It depends on how massive it is. It might become a supernova, and there is again historical accounts of the sky lighting up.
Yes.
I think the Crab was it the Crab Nebula or was it something else? I think 1000 AD or something, some Chinese historical textbooks or something like that. So apparently that coincided with the supernova explosion. So that's possible. Yes, but I do not believe that will wipe out humanity.
Okay.
Of course, there are many other ways of wiping out humanity. For example, a meteorite, a huge enough meteorite impact, or just ourselves through rapid climate change.
Yeah, I hope that will not come true. But
or of course also wars, right? Very efficient ways of destructing and wiping out humanity, which is a perspective that everybody should have as well.
Yeah. Mrityunjaya Mudali has raised his hand. Can you please unmute yourself and ask the question, Mrityunjaya?
Hello. Good afternoon, ma'am. Good afternoon, sir.
Good afternoon.
Yeah, good afternoon.
So my question is that, sir, why are the sunspots mainly located near the equator of the sun? Why not the poles?
Okay. All right. So you know something about the Sunspot cycle. So we wrote a paper in Science in 2002. That was my second paper of my PhD thesis, explaining that. And explaining that is then proposing a theory to explain that, which is one of the first theories which pointed out this issue that exists. Nobody really bothered to sort of look at, and we looked at it and proposed a theory, which is still debated. We still don't have a right answer to that question. Why are the sunspots usually located within roughly plus minus 30 degrees of the equator and not at high latitudes? The theory proposed was that there is a circulation which is observed, a large flow of plasma, almost like a river, large-scale circulation, known as the meridional circulation. It's somewhat similar to the Hadley cells, which is observed in the Earth's atmosphere. Nothing much is known about the deeper part of that circulation. in the surface, we see it to be moving away from the equator towards the polar regions. So diverging flow from the equator towards the poles. From mass conservation, you expect to see that, you expect physically that there should be also a large scale flow in the opposite direction, deeper down from the polar regions towards the equator. Otherwise, if this large scale meridional flow keeps happening over billions of years, then the sun will not remain a sphere, right? I mean, you're sort of stretching it out because you're not closing the circulation. So mass conservation dictates there has to be a return flow which closes the loop. So that was a proposal that this return flow has to be deep enough that it can reach the deep layers of the convection zone, where it can dredge the magnetic fields that produces sunspots into the region where there is not as much turbulence as there is in the convection zone, which is stable to convection, and which is a region where you can store magnetic fields without allowing them to escape, and then move them through the circulation, the counterflow of the circulation towards the equator, through the stable region. And the counterflow, which really is a loop, moves up near the equator, bringing these fields back up into the convection zone, where they can become unstable near the low latitudes and then emerge out as sunspots. So that's the technical theory that we had proposed and worked out through simulations, demonstrating that the hypothesis works in simulations. Since then, there have been multiple observations. There's a field of heliosismology, which uses very interesting field, which uses surface oscillations to image, to sort of invert and figure out the flows in the interior of the sun. And there have been strong controversies in the field about where does this plasma flow go into. Earlier, some people were claiming that this plasma flow is confined to near surface layers and closes in with multiple different counterflow loops. But more recently, I think there is a convergence that is emerging, that the meridional circulation is indeed one cell and goes deep into the base of the convection zone, as we proposed back in 2002 in that paper. But I must say that this is something that is still being debated.
Do you have any questions or clarifications, Mrityunjaya? You can ask that if you want.
No, ma'am, I'm clear.
Okay.
Thank you. Thank you, sir.
Any other questions? Do we have time for a few more questions? Vijayan sir?
I am here, so I can take questions for another 5-10 minutes, I think. If you have time, I'm okay.
Yeah. Actually,
I guess all of you are tired. It's been a long time, so but I'm good to take questions. I mean, yeah.
I also had a couple of questions. One is that you mentioned right at the beginning of your talk that there's this at the core there's hydrogen being converted to helium, and there's lithium and various other elements being produced, heavier elements. I always had the picture that in the sun, the hydrogen being converted to helium is the main process.
That is right. That's the main process. That's the primary process that goes on. There's a PP1 chain and there's a PP2 chain, but we also do produce some lighter elements in the process. But we don't produce anything beyond carbon. I mean, yeah, nothing beyond carbon we cannot go to.
Okay, but in principle,
but remember, the sun is born with some heavier elements from other stars.
Okay.
Like the supernova explosions, as I said, spews out heavier elements. So the sun has some heavier elements which it doesn't produce, but it's there, and so does the planet. And so the heavier elements that the sun cannot produce are all from the death of other stellar systems that we see.
Oh, so
that's the interesting thing. Yeah, it's all mixes up, and so I mean, we have many things the sun cannot produce, right?
But how does the heavier elements in Earth formed? It was
so they're not formed on Earth. That's the point I'm trying to make. Neither are they formed on Earth, neither are they formed on the sun. They have been formed in other stellar systems, and through the death of those stars and supernova explosions, which have been mixed up in the cosmos. These heavier elements come together and coexist with the interstellar medium, from which further gravitational collapse forms a star like the sun, which does not have enough mass and therefore not pressure and temperature required to produce the high mass elements, but can sustain nuclear reactions primarily to produce helium and some lighter elements. But the heavy elements have come from other systems. And those are the elements that find their way into planets and human bodies and play very important roles. So this is very important to remember that everything that we are made of, including planets, has not come from the sun. It has come from the interstellar medium through which the gravitational collapse formed the solar system and the sun and planets.
So that means the solar system kind of stuff would not have been possible to form even after, say, 200, 300 billion years of the Big Bang, right?
You mean million years, 200, 300 million years after the Big Bang. Yes, because the first stars, it formed about 1 billion years, and the first deaths of stars is supposed to have started happening around 10 billion years. So if you're thinking of life like us, I always use the word like us because you never know what life could be, right? So if you think of the human body and the elements that are there, we could not have existed in the first few billion years of the existence of the universe.
So what could be the few billion years means 6 or 7 or 8 billion years?
So current understanding is it takes about 10 billion years of the existence of the universe for the first deaths of stars and the first supernova explosions to happen.
Okay.
So if you're thinking of life like us, we could not have come into existence in the first 10 billion years.
Wow.
That's so amazing. Vijay sir, any more questions?
Now, when I say billion years, remember, this is all, we're talking in very astrophysical timescales in very qualitative ways. So give or take some, it's not precise science. Give or take, like, I mean, it could be 8 billion years also, right? Because these are all like, we're talking of timescales which are very
it's not the one single death of one single star. It will be
multiple.
No,
absolutely. Because you have to diffuse and mix it up over some vast scales.
The atmosphere, and it has been attracted and gathered and formed a mass, right?
Right, exactly. So that is also true, right? In the sense that by about 6-7 billion years, the universe was also very vast. So for certain, some deaths of stars would have had to happen in our galaxy, in the Milky Way galaxy, for things to have mixed up in the Milky Way galaxy also. For systems like the solar system and planets to have formed, which could have sustained life with the elements that have been born out of the local environment.
That's so interesting. Never thought of it like that before.
It is entirely connected. So
when we started off with it, expect me to give a talk about the sun, but I ended up giving a talk about the whole universe. But that is the fun. I mean, everything is connected to everything. We like to see science in isolation. We always think my science is better than your science. But then you really see, and when you think of in terms of the cosmos, you really see how many different science really comes together. And has this profound implications for our existence.
I had one more question. You said that about 400 years back, the Maunder minimum, in the 17th century, the Maunder minimum happened, and there are records of it from the observations of even Galileo and other people, of sunspots and all that. So how come these early observations are still preserved? And how do we connect up with them? How do we make sense of the data they had?
So there is a whole branch of science which is called archaeoastronomy, and also historical astronomy. It looks at historical observations. It looks at historical ways of observing the universe, and some of these observatories actually preserved the drawings. So there is, an interesting also socio-cultural political history which is connected with the scientific revolution that happened in Europe. I mean, usually you find that places which are the hubs of commercial hubs where there is a lot of money flowing through, which becomes the center of the world in terms of ideas and instruments moving in. Italy of those times was Venice particularly, and Italy was one of the hubs of cultural, economic hub of Europe. And a lot of merchants would use to travel through Venice because of commerce. And in one of those ships was brought this instrument, the telescope, which, by the way, Galileo was not the discoverer of the telescope, but rather inventor of the telescope. This was first perfected in Netherlands by people who used to build glasses like what I am wearing here. I think Hans Leppershey or somebody who built one of these first sort of telescopes. He was really a glassmaker for eyeglasses. And one of the sea merchants took it with him and brought it to a market in Venice. Galileo found it. And immediately he realized the importance of this in looking at distant objects. So he slightly tweaked it and modified his own and created his own version, the Galilean telescope, which he then used to do these observations. And at the same time, multiple other people were also sort of, not multiple, few others were also sort of inventing their own forms of the telescope and trading it on the sun, on the moon, on other planets, the moons of Saturn. Anyway, so those drawings became preserved. Many of those drawings are preserved. Galileo wrote books. Christoph Scheiner, another person who was a Jesuit priest working at the Vatican, he has this book called the Rosa Ursina, where he talked about all of this, preserved the drawings. And then from then on, in many of those observatories, documents started being preserved. And this is something that is fundamentally important. If you don't leave something behind in writing, if you're not able to preserve historical documents, and this I think is something that India should learn, you lose out in terms of the historical legacy in science or literature or anything else that you're leaving behind. And so it's very important for us to preserve what we have in terms of ancient Indian contributions also, I believe, which has been something that has been done by the Western cultures very well. You know, as soon as they produce knowledge, it's written down. It's not verbal. I mean, for a long time in Indian history, it was verbal, right? Things passed down verbally. But the importance of having written history is so important. So for a long time, it was actually preserved in different observatories in around the world, such records. Then scientists who work on historical astronomy got together and brought together all these different observations, literally drawings. And I have these drawings. I mean, you can actually just do Google search, Galileo's drawings of sunspots. Just do a Google search. You will actually find Galileo's drawing of the outline of a sun with the spots sort of drawn on that. Oh. So from those drawings, people started figuring out the number of sunspots, and they would be dated. The drawings would be dated. They started figuring out how many sunspots were there on the sun from the times of Galileo until when we had observatories which were dedicated to observing sunspots, which was something around 1870s. And before that, it was sort of reconstructed from these drawings. And from that, we have now built up this historical picture. That's one way. There is another very interesting way of figuring out past solar activity that is based on cosmic ray records. If you look at the low energy cosmic rays, they are actually modulated by the magnetic field, interplanetary magnetic field. The magnetic field from the sun that is taken out by the solar wind and permeates the solar system. The flux of galactic cosmic rays, the low energy galactic cosmic rays, is influenced by the magnetic fields in the solar system, which is directly connected to the sunspot cycle. So when the sunspot cycle is strong, the interplanetary magnetic field in the solar system is strong. It traps more of the galactic cosmic rays. So the galactic cosmic ray flux on Earth is smaller. Now, the galactic cosmic rays, through a series of reactions called spallation reactions, creates an isotope known as the beryllium-10 isotope. It's a cosmogenic isotope. It's known as a beryllium of cosmic origin, beryllium-10 isotope in the Earth's atmosphere. The beryllium-10 isotope has a long half-life. I forget again. I'm not good at numbers, but I think, well, I don't want to just say out a number, but I think it has a very large half-life, which is enough to be able to reconstruct the abundance of beryllium-10 over on the scale of 10,000 years.
Oh.
Now, the beryllium-10 isotope gets absorbed in snowflakes. And when a snowfall, it reaches Earth, right? Now, if you're in India, that's not, or somewhere in Darjeeling or Shimla, it's not very helpful because you have snowfall and then it melts away. It is not very helpful even if you're in New York because you have snowfall, it melts away. It's not helpful to have snow which is lost. It's helpful to have pristine snow which gets which gets preserved, right? That happens only in the regions around the Arctic, in Greenland and in Antarctica.
Okay.
Snow falls and it gets connected, coupled. You have snow from previous times, more snow on top, more snow on top, more snow on top. And there are people, and this also happens. So the US is a pioneer on this. Also at the what is this institute in Goa, National Center for Atmospheric and Oceanic Research or something? They also collect this ice cores. You can go to Greenland, you can go to Antarctica and dig deep.
Is it NIO? National
Yes.
Institute of Oceanography.
National Institute of Oceanography, exactly. Thank you. You can go and dig deep and collect a cylindrical tube of ice. The deeper part of that ice contains beryllium-10 collected from the atmosphere during the snowfall thousands of years ago. The toppest part is the most recent snowfall, which has the most recent abundance of beryllium. Also contains oxygen-10, whose formation depends on the temperature. So actually, you can get these isotopes, sample them from different depths of this ice core you collect, and then invert back to figure out the magnetic field, the cosmic reflux, the magnetic field in the interplanetary medium, and the sunspot numbers on the sun. Similarly, you can use the oxygen-18 isotope, which is dependent on the global temperature to reconstruct global temperature.
Wow.
And then you have a scientific way of utilizing all of this to figure out past solar activity as well as past climate report. And I find that absolutely brilliant, actually. I mean, it's amazing.
It's stunning.
In each of those expeditions, I know the US spends a few $1 million to collect an ice core, preserve it, and take it and then put it in a vault so that, in the facilities in Boulder so it doesn't melt. And then you can take out small samples from there and do different science out of it.
Stunning.
Wow.
It is stunning, absolutely stunning, actually.
Mm-hmm.
Yeah.
Yes. That means the beryllium is floating on the air, atmospheric air, and it is when the snowfall happens, it's getting collected and frozen inside the surface, right?
Right. And then if it's pristine, if it's not contaminated, like it happens in very remote areas in Antarctica and Greenland, you can go and dig and collect that ice core, which is really a cylindrical tube of ice, and you have that whole history.
But you continue to get the beryllium from the cosmic stuff.
Cosmic
right?
rays.
Right.
The formation of beryllium-10 isotope depends on cosmic reflux hitting the Earth's atmosphere and creating this set of reactions called spallation reactions to create the beryllium.
You still get the beryllium-10?
You still get the beryllium.
Oh,
yes.
Thank you so much. Are there any other questions? If not,
I think we should arrange for a Meet the Scientist program with Dr. Dibyendu, because there are many students who may be interested, interact with him to gain more, and they can choose their career, right?
Yeah. Actually,
I'm happy to do that sometime.
Yeah,
that would be wonderful.
Sure.
Wonderful.
So we want to become a children and we want to go back as a student and want to learn. It's very interesting. Anyway, we are.
One more question from in chat.
Yes, in the chat box. How does the solar neutrinos behave during CMEs? Are they expelled in huge numbers or are they the same?
Okay, so the solar neutrinos are created in the sun's core, whereas the CMEs are produced in the sun's outer atmosphere. The amount of magnetic field that is there in the CMEs is too small to couple to the neutrinos. So the solar neutrinos are more or less independent of what is going on in the outer atmosphere to the coronal mass ejections or flares that's coming on. Solar neutrino flux, it's produced in the core, in the nuclear reaction that's happening there. So it's a probe of the core, but not of the physics of the outer layers. I was just talking to Bishwarup just a couple of weeks back here, and I know that I also had this conversation with the Brazilian particle physicist. And of course, this is not a field I understand very well. The particle physics, the coupling of neutrinos to magnetic fields. But there is some thought, which is not something that is very well evolved, but they're thinking, that community is thinking, that there is a coupling possible between neutrinos and magnetic fields, which can alter the neutrino flux. And we have talked about that. And I am thinking if they can actually evolve and mature that theory, then that could become a useful probe of the magnetic fields, the stronger magnetic fields, which are deeper in the interior of the sun, which as of now, we are not able to probe observationally, and our ideas are completely based on theoretical models.
Okay. Does it answer your question, Raj? Yes. So any other questions? If not, Vijayan sir, can you?
Yeah, we can wind up, and it's the time for Chella Kumar to deliver the vote of thanks. Chella Kumar.
So can you hear me?
Yeah, yes, sir.
Good afternoon, everybody. On behalf of the Popular Science Lecture of Tamil Nadu Science Forum, I extend my thanks to our respected speaker, Professor Dr Nandi from ISA Kolkata, to take out time from his busy schedule to grace the event. Thank you, sir. Thank you for your excellent and interesting lecture about the sun and its dynamics. A special thanks to Dr. T.R. Govindarajan and Dr. Subhashri for providing immense support to make the webinar successful. I extended my thanks to Mr. Vijayan, Mr. Sundar, Mr. Chibi, and all my colleagues in the PSL Executive Committee to organize this webinar successful. I must thank to the audience for listening to the webinar and their cooperation. Thank you, everyone, once again for making this session a great success. Thank you.
Thank you for hosting me. It was a pleasure talking to all of you and interact with the
Thank
audience.
you very much. Now we will meet again, sir. So we'll come back to you again.
Yeah, just call me Dibyendu. I think that's just fair enough.
Right, sir. Okay.
Thank you very much.
Thank you.
Bye-bye.
Thank you.
Bye.
Bye.